Okay, good morning, not even morning anymore. Okay, so today I'm going to speak about the toughness of very ductile steels used for pipelines. This work is actually part of the PhD work of Takahiro Sakimoto, who's now working at PFE in Japan. So what is the context of the motivation of this kind of study? So we are working on very, very ductile, modern pipeline steel, which are very ductile and very tough. So that it's very difficult to obtain J data acres which are valid according to the standard, for instance, the ASTM standard. So the basic idea of this work is to use some kind of damage model. In that case, we're going to use the GTL model. We are going to fit it on an experimental database which contains a lot of specimens. And then we're going to use this model to perform virtual testing. Because if we can make a model, a FE model of any CT specimen, we can, for instance, take a very large CT specimen that you cannot machine because your pipe is too thin. But at least you can numerically produce it, simulate it, process it according to the standard, and get something that you can call a valid J delta acre. So this study was done on this material, so it's X65. It was supplied as a plate, and its thickness was slightly below 30 millimeters. Microstructure is quite standard ferrite granite. As I said, it's a very modern steel, so the sulfur content is very low, and we have a very low inclusion content. And these inclusions, which are nitrides or sulfides, they are the sites for ductile damage initiation. Our evaluation of the volume fraction is 10 to the minus 4, so that's very low. Let's make, for instance, a tensile test along the T direction. That's the low transverse direction of the plate. So there's a little bit of Wheeler's plateau here, hardening. And then you can compute the effective yield strength, which is the average of the yield strength on the UTS. So we get something like 588. And then we can use this value to compute the Jmax value that you can obtain for a valid test according to this standard. Here I've done the calculation for a specimen with a thickness B equals to 12.5 millimeters. And that gives me this value for the J limit and the corresponding KJ value. So it's about 600 kilojoules per square meter, which appears to be quite high. Okay, so here's one test on a CT specimen. So as I said, that's the thickness. We use 10% side grooves. We've done the same on SCNT specimen, which I'm not going to report in this presentation. And we introduced a crack as an EDM notch because the material is so ductile that using a very fine EDM notch with a diameter of 100 microns is really equivalent to pre-cracking. So the initial EDM notch is about here. That's ductile crack advance, and the specimen were afterwards broken in liquid nitrogen, and that's this area here. What is obvious in this picture is that the specimen is very heavily deformed. Ahead of the initial crack tip, you see quite a lot of necking, and even the side grooves are deformed. So here are two tests, for instance, and experimental J delta acre. There's no computed J delta acre on this one, but let's crack advance that J. So you get a pretty linear curve, really corresponds to blunting. There's a little bit of deviation here. And you start to have deviation for values of J above 1,500 kilojoules. So that's way above the limit that you are not allowed to exceed if you want your test to be valid. So that's a problem, because if you reach this point, actually there's no crack propagation. It's just sheer blunting. That's the problem. So the one solution could be, okay, well, don't use this material. Too good, we cannot apply standards. But that's not true in these 3 months. Okay, so the solution here is maybe virtual material testing. If we want to do virtual material testing, indeed, we need model. And for this material, we need a model for plasticity and a model for ductile damage. I won't go into these equations. You see they're gray so that you cannot read them. I only want you to look at this photograph here. That's the fracture surface of a tensile test performed in this material. And you see that the fracture surface is a nice ellipse here. That's really indeed the specimen was machined as a pure cylinder. That really show you that these materials, when they are supplied as plates, they can be very, very anisotropic. And I really think it's no use trying to apply any damage model with such a level of plastic anisotropy if you don't attempt to model that. Because the stress field that you may use neglecting plastic anisotropy may be very wrong. So here, in this work, we use the model we developed quite a long time ago now. It was initially developed on aluminium, but we use it also to represent the behavior of such plate materials. And then we have to move to the damage model here. There was not a big effort done. We just used the standard GTN model. The only modification that we introduce is that here, instead of using the mesostress, we use the anisotropic stress measure we have defined before. Otherwise, everything here is really following the standard GTN modeling with the F star function for description of coalescence and final failure. With these values, which are not Q, we just choose Q1 and Q2. With this material at high tracicity, there is no need for nucleation, so it's fairly simple. And then we apply normality to get the flow rule on the evolution of porosity, which is damage and hardening. And that's the straightforward Pearson model. So here are some examples of the fits. So for instance, we perform tests on axisymmetric notch bars with different radii. So NT10 is a gentle notch, NT2 is a very severe notch. And the experiments are lines, and simulation are the dots. So you see there is a fairly good fit. You see that in the simulation, as in the experiment, there's a lot of necking, and you almost completely destroy your initial notch. And in particular for NT10, you see that once again, the fracture surface is not round, it's like an ellipse. Not as pronounced as with the tensile test, but nevertheless, it is an ellipse. So all this calculation has to be 3D indeed. Some other example, for instance, here we used a plane strain specimen. So once again, we have a very good fit between experiment and simulation. If you consider plane strain specimen, that's where the load parameter is around 0, but here it seems that we can fairly describe this specimen without the need for introducing a load dependence of the model. This is a specimen, it's a flat specimen with notches, and we get also good agreement. And this specimen is somewhere in between in terms of stress reactivity and load parameter between the plane stress and the axisymmetric specimen. So let's move to the CT specimen. So here are my two CT tests with partial unloading, which is used to compute or evaluate crack advance. It's always interesting to get the simulation without damage. That's the red curve, which is above indeed the experiment. And the black thick curve here is the simulation, and we get a fairly good match, not as good at the end, but the beginning at least very good. That's one snapshot of the simulation. You see that there's a lot of crack opening, and that when you look at the experiments, it's just like that. It's so ductile that if you look at the compression side of the CT, we have side grooves, but the side grooves they are going into compression, then they touch each other. So there's something like a side groove closure on the compression side, which is you can see it. I don't have a picture of that, unfortunately, but you can really see it in the experiment. That's the same kind of results with the SCNT. So once again, we're very lucky we can have a very good fit with this simple model. Here we also model some kind of extension, because these experiments were done with a double click method proposed by Exxon, so we just mimic it in the simulation. That's why we get these two small antennas. And here once again you see that crack opening is just huge, and a lot of necking ahead of the crack front. Okay, so now the basic idea is we can run simulation by mimicking the unloading compliance method, just as in the experiment. And that's one way to measure delta A. For this curve, for instance, we have CMOD and force with partial unloading, but these partial unloading are actually simulated, because when the crack propagates, elements are removed and the stiffness of the specimen is going down. You don't see much because indeed there is a lot of deformation. You don't see the stiffness variation. There is a stiffness variation on this simulation. So basically, we have a program which we use to process the experimental test. We just use the exact same program to process this simulation. So there's no interpretation needed. And here's the result. So that's the same curve as before. Blunting line, the limit. We have two experiments, and the thick black dots are the simulated curve, which is processed using the program used for the experiment. So I just process this data here and get the J data, simulated J data curve. Indeed, as you've seen that the match between experimental and simulated CMOD force is very good. And indeed, this leads to a very good correlation between experiments and simulation in terms of J delta curve. So we can also process this calculation to evaluate delta A. That's an arbitrary unit for loading. So the thick dots here is the crack advance we get with the unloading compliance method applied to the simulation. The small black dots is what you get if you neglect the correction for rotation. So you see at the end you can have a fairly big error. And the red curve here is what you get when you process your simulation as in the standard using what's called the 9-point method. So you actually measure the actual crack, where that is actually broken, not blunting. So indeed, at the beginning there's no crack advance, there is blunting. But the unloading compliance method gives you some kind of crack. And after that, here you get really crack initiation in the simulation. So you start removing the elements and the crack is growing, but it's always slightly below the crack advance you get from unloading. So now I can use this method to obtain a valid J delta A curve. So my aim, for instance, here is to reach a limit J value of 2,500 kilojoules per square meter. So to do that, I need a specimen which is 50 millimeters thick. My plate is below 30 millimeters. There's no way to do this test. So that's my mesh for the 12.5 CT, and that's my mesh for the 50 millimeter CT. You don't get this mesh just by applying some kind of homotherapy to get here from here, because we are dealing with damage, crack propagation, and if you're dealing with damage, crack propagation, there is an internal length. Here we're not using non-local damage model, which I'm working on. By the way, it's difficult to do this calculation with such models. So the trick we use, which many of us use, is to use a fixed mesh size of 100 microns. So here basically you get much more elements than here. But in the region where the crack is going to propagate, you use this fixed mesh size. So here I plot the force versus CMOD, but normalized by the specimen width and by the specimen initial cross-section times the UTS, basically. So if there is only plasticity, the two curves, the two specimens should exactly be the same. But because of damage, because of localization, because of internal length, as soon as the crack propagates, it's about here, you get a difference. So the blue curve is for the thick CT and the black curve is for the thin CT. In both cases, we have simulated partial unloading to get the J delta A curve, and that's the result. So that's the result of the comparison of the two simulations. So the black dot is a 12.5 CT, the blue dot is a 50 millimeter CT. And here you have the validity limit. So my 50 millimeter CT is valid. It was designed for that purpose. What I did not really expect is that the difference between the two specimens would be so small. I'm quite surprised, so I have to repeat that, maybe do a CT100 and do the same kind of job on SCNT. Okay? But if it's true, if I can confirm that, that's somehow good news, because it's very close, and the CT12.5 gives you some kind of lower bound, so which is on the safe side from an engineering point of view. So, conclusions, so we have been studying this pipe and steel. We use the GTL model with void growth only, and it's working. We use this virtual material testing to obtain valid J delta A curve, and as I said, we have to do that with SCNT. The real problem is when we want to go down to very small size specimen. For instance, specimens that are extracted from a pond that you can get in situ. And you get CTs that are like that. And with the constant mesh size, you start to have very few elements within the ligament. That's possibly a problem, and I think that's really where you need an overall model.